So good morning. So my name is Janaína Mourão Miranda. I'll be co-sharing the multivariate approach to modeling and analysis section with Arpan Banerjee from National Brain Research Center in India, and I'm from University College London. And the first speaker of the session is Johanna Bayer from Dundas Institute for Brain, Cognition and Behavior. Please.
Just to add that you can... So you can ask questions through the audience response button. We are checking that, as well as there's a microphone in the center of the room.
Okay, thank you. How do I advance the slide? Here, right. Yeah. Thank you for the invitation. I have no disclosures. So if you've been around for the last 5 to 10 years, then you've experienced the dream story that normative modeling is. From the first publication of the framework to the first release of pre-trained models, there's been a great uptake. And I'm only showing here other papers that have also released pre-trained models, not to speak of all the applications to papers that have been published applying this framework. If you've not been around for the last 5 to 10 years, then just a quick catch up what normative modeling actually does. So what we're trying to do, usually we are interested in explaining the variation in a feature, for example, the volume of the left lateral ventricle by covariates and batch effects. That could be age, sex, and size. And what we do if we only train a normative model is we derive these so-called distance centiles. These are lines that divide our feature space based on the variation that the data points of the feature fall under. So for example, you see here the median, the middle line, that divides our feature space in a way that we have 50% of the variation above and 50% of the variation below the median. And if we train a normative model on healthy controls, what we can do is we can take a different population, for example, a clinical population with features that we're interested in, and we can see where these individuals fall within the centiles that we've trained derived from healthy controls. And that's very useful because we get a Z-score of deviation per individual, and we can use that in downstream analysis. So far, so good. But up to now, normative models have exclusively been trained on cross-sectional data points. That means that one subject provides one data point. And let's now move away from that. Let's move to longitudinal measurements. So let's assume you have a clinical subject and you measure this subject repeatedly and you plot their trajectory into this distance centile framework. And I'll tell you in a second why I call it distance centiles. You measure the subject 3 times and you see that they're tracking the median quite well. And then you measure a 4th time and you see that they're actually moving away from the median. The question is now, is this 4th measurement different from the previous 3? And as a matter of fact, you can actually not make this judgment call based on this distance centile framework that we've derived. What you really need is a new measure that quantifies the normative rate of change. And in order to get this measure, you can only get this measure by using longitudinal data. And what you need to do is you need to take a healthy subject and, again, measure them repeatedly and plot their trajectory through this distance centile framework. And what you can then derive is a new measure, like I said, so-called velocity centiles, that quantify the normative rate of change across the lifespan. And this is also why I call the other framework distance centiles, because velocity is the first derivative of distance, so we kind of borrowed this term from physics. Once you've done that, you can create a new chart, a velocity centile chart. And once you've done that, we can go back to our clinical subject. And we can actually go one step further. We can calculate so-called thrive lines. Thrive lines is basically the cutoff point of a velocity centile that kind of marks the amount of change that basically makes the change significantly different. So a change that is associated with a Z-score of 1.96 plus minus. And if you have like a thrive line, basically a thrive line distance, that means that the change that the subject has experienced is like in the 5% of abnormal changes. So once we have that, we can go back to our clinical subject and we can plot it again here in these velocity centiles, and then we would see that our 4th measurement is actually in the extreme amount of change. So talking about how do you derive these velocity centiles, and there's a couple of issues associated with that, and I'm not going to talk about all of them, But I wanted to touch on two, and the first one is what I call conditional reference, and it's the idea that if you want to calculate velocity centiles, you cannot do that, you cannot use the absolute amount of change for like two reasons, and that is that the absolute amount of change is actually conditional. It depends on when you measure and what your starting point is, and I try to illustrate that here. So you see here three identical changes, and in C, you see that the subject basically tracks a distance centile. But if you move up and have a different starting point in B, this subject crosses the centile. And if you measure in a different developmental period, you see that the subject moves away from a centile. So basically, your absolute amount of change depends a lot on where you are and when you measure. And it's kind of related to this other idea about centile crossing, that from a distance centile chart, we do not really know how like healthy subjects move in this chart. So we do not know, do they track their centile or like do they move away? Is that healthy? We just do not know. So we need to measure that. In order to, like I said, if you want to calculate velocity centiles, you need to do that from z-scores. Luckily, we have normative modeling, so we have a way to get z-scores, and that's what I did. So I trained a normative model on healthy controls using our SHASH framework that can deal with known Gaussian distributions. And I got z-scores to deal with this conditional reference. This is my training set, so I trained my normative models on a large cross-sectional data set, and then I had a very carefully put together test set that also contained cross-sectional data, but also a lot of longitudinal data. And here you see this distribution of follow-up points in the longitudinal data. So we had up to 6 follow-up points. And then I had also clinical subjects because I wanted to validate it in Alzheimer's, actually. And then you see some results. So this is the left lateral ventricle, and you see here in black, these black lines, like these dotted lines, is just a traditional distance centile chart. And then you see these blue shaded areas, and the way you read this, maybe I'll move over here, like if you're here, in the next 2 years, you're not meant to move away or move outside this blue shaded area. And if you do, basically the amount of change or deterioration that you get is abnormal. Of note, these blue shaded areas, they are like vectors. You can plot them in any point of this distance centile chart, and you also see that they actually change basically in length and direction, which kind of takes care of this conditionality. So it maps basically the underlying amount of change in healthy subjects. And you see this black dotted area, that is actually in Alzheimer's subjects, a 2-year follow-up, and I didn't even bother to plot, to anchor my distance centiles at the origin of this subject, like on the first time point, because you can see that this subject crosses this blue shaded area by far. And you can also do, this is like for the left lateral ventricle, I plotted upward stripe line, because the left lateral ventricle deteriorates or gets bigger as a function of disease. For other regions, and I did it for all the free surfer regions, you can plot downward stripe lines. Again, the CSF would make more sense for upward stripe lines, but you can do that for all of them, and they look very differently. You can do other really cool things with thrive lines. So, like I said, thrive lines have basically a z-score of 1.96 associated to them, but if you have 2 measurements, you can also just calculate the z-score associated with this change. And I did that here for healthy controls and ADNI subjects, so clinical ADNI subjects. And you see in the first plot over there, the so-called Z-gain score, there's the Z-score associated with the change. For healthy control, it kind of is like a nicely formatted Gaussian around 0. And for ADNI subjects, it's first of all, the distribution is far more widespread, but it's shifted toward a negative Z-gain. That means basically that for the left hippocampus in this example, ADNI subjects, basically their campus size decreases faster than healthy controls. What you can also do is you can plot the Z-gain score as a function of disease status. That's the second plot. And you see here, like again, for healthy controls, we have a Z-gain around 0. Then for subject with EMCI, it's shifted toward negative Z-gain, and for Alzheimer's, even more. And then in the third plot, which is, I think, the most interesting, you can also plot Z-gain as a function of change of disease. And you see here, first I had subjects that have Alzheimer's at the first time point, and then also at the second time point. Then I have, in like lighter red, subjects that have EMCI and transition to Alzheimer's. And then I have subjects that have EMCI and stay at EMCI. And you see that the subjects that transition, actually, they have like the same Z-gain distribution as the subjects that have Alzheimer's and stay with Alzheimer's compared to the ones that don't transition. So this is really like an indicator that maybe Z-gain might be sensitive to actually predicting change to Alzheimer's. And so I conclude from this that information derived from longitudinal normative models, such as thrive lines and z-gains, are sensitive to detecting clinical change over time. Healthy individuals exhibit variability around normative centiles, but in clinical subjects, this variability is much more widespread. And classical distance centiles cannot provide information about change over time. Rather, it is essential to base these inferences on velocity centiles derived from normed longitudinal data. And I thank my colleagues, Augustin de Boer and Hannah Savage, and my supervisor, André Marquand in Nijmegen. Thank you.
We have one question in the app so far, which is incredible interesting technique to expand normative modeling. So are you using a particular package to perform this analysis?
Yes, we're using the PCN toolkit of our lab. So that's a normative modeling toolbox. And yeah, it has this, like I said, the non-Gaussian distribution, the Schacht distribution normative model. And we're also going to add the thrive lines. And we're also going to release all this data. I just didn't get it finished on time. And there will be a paper as well, very soon.